Section 2.8, Curve Sketching. Our objectives are 1. Use the first derivative to find intervals where a function is increasing and where it is decreasing. 2. Use the second derivative to determine where a function is concave up and where it is concave down. 3. Find inflection points. And 4. Connect graphs of functions with graphs of their derivatives. The definition of a function increasing or decreasing follows. The function f is increasing on the interval from a to b if, given any 2 points in the interval, the function evaluated at the smaller value of x will be less than the function evaluated at the larger value of x. In other words, if as x gets larger and larger, f of x also gets larger and larger, so something like that, this function is increasing the whole way. The function f is decreasing on the interval from a to b if, for any 2 values of x between a and b, that implies that the function evaluated at the smaller value of x, that is to the left, is greater than the function evaluated for the larger value, that is the one to the most right. So something like this as x gets larger and larger, f of x is getting smaller and smaller. Graphically, a function is increasing if, as we move from left to right, the height increases. The function is decreasing if, as we move from left to right, the height decreases. I think that was made clear when I made these little sketches up here. Let's look at some examples. So let's say I've got a function here doing all kinds of things. Here, the function is increasing, and I'm going to go ahead and put some arrows on here, so that tells us we're going to infinity in either of those directions. So the function is increasing because it's getting higher and higher until we get to here. And then it is decreasing until we get to about here. And now we're increasing. And now we're staying the same, so constant. And now we're increasing again to here. And now we're decreasing. So let's throw some labels on here. So we'll just call this A, B, C, D, E. So intervals where we're increasing from negative infinity to a, so negative infinity all the way to here, we're increasing, and then we're decreasing, and so I might as well just write everything as we go through it. Intervals decreasing, we'll put underneath. So from infinity to a, we're increasing. From a to b, we're decreasing. So from a to b, we're decreasing. From b to c, we're increasing again. I'm going to use the union symbol to connect the intervals. From b to c, we're increasing. From c to a, we're constant. And that would include the endpoints. And then from D to E, we're increasing again. And from e to infinity, we're decrease again, so union e to infinity. So we're using the interval notation and the union symbol in order to identify these intervals. Let's keep going. First derivative information, part 1. That is, what the function tells you about the derivative. For a function f, which is differentiable on the interval from a to b, so differentiable just means the derivative exists in this interval. If f is increasing on the interval, then the first derivative will be positive for all x's in the interval. If f is decreasing on the interval, then the derivative will be negative for all x in the interval. If f is constant on the interval, then the derivative will be equal to 0 for all x in the interval. Now the converse is also true. First derivative information, part 2, what the derivative tells you about the function. For a function f, which is differentiable on an interval from a to b, if the first derivative is positive for all x in the interval, then the function is increasing on that interval. If the derivative is negative for all x in the interval, then the function is decreasing on the interval. If the derivative is 0 for all x in the interval, then the function is constant on that interval. This is the same thing as saying the slope equals 0. If we say the function is constant, that means the slope is 0 on the interval. Example 1. Consider the function f of x equals 1/3 x cubed minus x squared plus x plus 1. Consider your expectations of the graph of this function. I can see that the function is a cubic. I can see that it has a positive coefficient. So it's going to look something like this. But what's going on in the middle here could be flattened out and look more like this. So when I'm looking for intervals where the function is increasing and decreasing, I expect it to be either increasing, then decreasing, then increasing, or just be increasing the whole time. Find the critical numbers and determine where the function is increasing and decreasing. Then consider what you expect of the graph of the derivative and graph both. So first, let's find the derivative. So 1/3 times 3 would be 1x squared minus 2x plus 1. The derivative of 1 is 0, so we're done. Now let's find our critical numbers. Critical numbers are the x values, where the derivative is 0. So x squared minus 2x plus 1 equals 0. Oh, nice, it's easily factorable. And I can see then x must be equal to 1. So we only have one critical number. Now let's go ahead and make a sign chart. And 1 is the critical number. That is the x value where the first derivative equals 0. And I'm going to look for information about the first derivative to give me information about the function. I know that if the derivative is 0, then the function itself is horizontal at that place. And now I want to check the intervals to the left and to the right of my critical number. So I'm just going to check at 0 and at 2. So at 0, that is f prime of 0. Sub 0 in here, 0, 0 is 1. So this is positive. At f prime evaluate 2, 2, 4 minus 4 plus 1 is also 1. So this is also a positive value. So this is telling me the function is increasing the whole time. That tells me I'm expecting the graph to look something like this, flattened out, increasing the whole time. What do I expect of the graph of the derivative? Well, the derivative is a quadratic, so I know it's a parabola. The coefficient of the squared term is 1, so I know that it opens upward. And I know that I have a y-intercept at the point 0, 1. I know I also have a y-intercept at the point 0, 1 in the original graph. So let's look at the graphs now. So I'm going to put in the graph of the original function first. And I'm going to go over here, and I'm pressing enter repeatedly to get some kind of a distinction. We'll use this dotted line to see if that shows up good enough to look at the graph of the derivative. So we're going to look at both of these. So the line is the function, and the dotted line will be the graph of the derivative. And of course my window is set to something strange from the last thing I did on it. So let's go ahead and go zoom standard. Aha! So here's my graph, looking just like we expected. And here is the graph of the derivative. It is a parabola, and the vertex of that parabola is the same as our critical number right here. So here's the graph of the function, and here's the graph of the derivative. And this point is that point. And you probably noticed that is the x-axis here. Every value of the derivative is positive because the function is increasing the whole time. Here we have a pretty steep slope that flattens out. So that means a steep slope is a greater value. So that's why we've got positive values that are getting smaller and smaller because the slope is getting less and less steep. And then here the slope gets steeper and steeper. And there we go. Second derivative information. A function is concave up on an interval from a to b if and only if the second derivative is greater than or equal to 0 for all x in the interval. A function is concave down on an interval from a to b if and only if the second derivative is less than or equal to 0 for all x in the interval from a to b. So the double-headed arrow tells you the logic is working in both directions. So the function is concave up on the interval, tells you that the second derivative will be positive for all x in that interval. On the other hand, if the second derivative is positive for all x in the interval, then the function is concave up. And I think they're only putting in the or equals here if we were at the endpoints. Inflection point definition. An inflection point is a point on a graph where concavity changes. Possible inflections occur at x equals a, where the second derivative evaluated at a equals 0, or undefined. So, example 1, let's go back to this same graph. Notice when we look at the graph, although it's slight, this is concave down, and this is concave up. So based on our visual look at the graph, we expect the interval from negative infinity to x equals 1 to be negative, evaluated the second derivative, and from 1 to infinity, it's concave up, so the second derivative to be positive. So let's check it out. So from the graph, do we expect any inflection points? Yes. I'm just going to resketch this here. So this point here is where x equals 1. Concave down, concave up. I expect an inflection point here. Find the possible inflection points and determine where the function is concave up and concave down. So recall, this is our derivative. So let's find the second derivative. And let's set it equal to 0. And not a surprise, our critical number for the second derivative is also x equals 1. So we'll make our little chart. And now we're going to let information about the second derivative tell us information about the function. So at 0 here, we are neither concave up nor concave down. I'm going to evaluate the second derivative at 0 and at 2. So at 0, the second derivative is negative 2. So negative, which tells me concave down. And I'm going to evaluate at 2. And I sub 2 in here. 4 minus 2 is 2. So positive. So that tells me it's concave up. So this graph is concave up on the interval from 1 to infinity and concave down on the interval from negative infinity to 1. Let's go back up to the first part again because I did not make note of where the function is increasing. F is increasing on the interval from negative infinity to infinity. That is all the real numbers, every x in the domain. Let's continue and work another example. Example 2. Consider the function f of x equals 3x minus 2 over the cubed root of x squared. Find the possible inflection points and determine where the function is concave up and concave down. So the first thing I'm going to do is translate this function into exponential instead of root notation. That'll make it easier to calculate the derivatives. So 3x minus 2x to the negative 2/3. Okay, so then the first derivative would be 3 plus 4/3 x to the negative 5/3. And the second derivative would be, derivative of 3 is 0, so negative 20/9 x to the negative 8/3. Now to find our possible inflection points, we need to check where the second derivative is equal to 0 or undefined. I'm going to go ahead and rewrite the second derivative now with root notation because it'll make it easier for us to see what's going on. So we can rewrite this as negative 20 over 9 times the cubed root of x to the 8th. Now I can see here the numerator can never be 0. So the second derivative is never going to be equal to 0. But I can also see that where the second derivative evaluated at 0, if x is 0, the denominator is going to be 0. So the second derivative is undefined at that point. And that is our only critical number. So we'll make our little chart, and then we'll make it easy on ourselves and evaluate at -1 and 1. We're looking for second derivative information to tell us about the first derivative. And here we are undefined. So if I sub in a -1 here, -1 to the 8th power would be 1. This is just going to be -29ths. So this is going to be a negative number. So that tells me concave down. But if I sub in a +1, that's also 1. So this would also be -29ths. So it's also going to be negative, concave down. So this shows me F is concave down from -infinity to 0, union from 0 to infinity. So let's take a look at the graph. The reason I excluded 0 is, look what's going to happen if we plug in a 0 here. This will also be undefined. So we need to leave that out. We just can't say it's concave down everywhere. We need to make sure that we cut out the 0. Let's do another example. Consider the function f of x equals x squared e to the 5x. Find the possible inflection points and determine where the function is concave up and concave down. So our function is x squared e to the x, or e to the 5x. So our derivative, we're going to need to use the product rule. So our derivative would be the derivative of the first, 2x, times the second, e to the 5x, plus the derivative of the second function, so 5e to the 5x, times the second function, times x squared. And I can regroup this a little bit. Usually, I'll put the x squared in here. And if I want to find the second derivative as is, I'd have to use the product rule on the first term and then use the product rule on the second term. So I'm going to do it a little bit differently. I'm going to rewrite this, and I'm going to pull this e to the 5x out front and regroup. So now I just have to use the product rule once to find the second derivative. So the second derivative would be 5e to the 5x times 2x plus 5x squared plus e to the 5x times the derivative of the inside, so 2 plus 10x. And now I want to factor out the e to the 5x. And we'll go ahead up here. So I'm going to distribute the 5 first. And then I'm going to simplify this as much as I can. So I've got a 25x squared plus 20x plus 2. And now I'm ready to find my critical numbers, and that would be setting this equal to 0. Now, e to the 5x can never be equal to 0, so we can ignore that. I need to focus on where is this equal to 0. And I play around with factoring, and I can't factor it, so I'm going to use the quadratic formula. So my a is 25, my b is 20, my c is 2, and so x would be negative 20 plus or minus the square root of 20 squared minus 4 times 25 times 2 all over 2 times 25. And let's see what kind of values we get. So negative 20 minus the square root of 20 squared minus 4 times 25 times 2, all divided by 50. Going to 4 decimal places, and then negative 20 plus the square root of 20 squared minus 4 times 25 times 2, and divide all of that by 50. So going to 4 decimal places, negative 0.1172. And now we want to check these values. So I'm going to have to move up here to do a sign chart for example 3. So looks like negative 1/2 is between these two. And 0 is definitely higher than both of them, and negative 1 is lower than both of them. So I want to try negative 1, negative 1/2, and 0. And we're using the second derivative to give us information about the function. So let's go ahead and put in our function. So we remember we're evaluating the second derivative at these values. So we want to go ahead and put in second ln gives us the e to the 5x times 25x squared plus 20x plus 2, and we can go ahead and use the table. And I notice if I put in, let's see, we wanted to enter negative 1. This was our critical value. We should get 0 here, so let's see, negative 0.7453 about. Do I get something darn close to 0? Kind of. 0. Whoops. Negative 0.5. I wanted to check. And negative 0.1172. That should be darn close to 0. And it definitely is getting even closer to 0. And then I wanted to check 0. Okay, so the values we found so far is the second derivative. We expect to be 0 here. At negative 1, we were positive. At negative a half, we were negative. And at 0, we were positive again. So this tells me that my function f is concave up to the right of this number, concave down between our two critical numbers, and then concave up again. So I could write concave up from negative infinity to negative 0.7453 union 0.1172 to infinity, and concave down on the interval from negative 0.7453 to negative 0.1172. And we've just found our intervals of concavity. One more thing to look at for this section. We want to connect graphs of functions with graphs of their derivatives. The derivative of a function is a function, and you can graph it. Since the derivative at any particular point is the slope of the graph at that point, you can examine points for key characteristics to figure out the graph of the derivative. Some of the key characteristics you're going to look at are, 1, if the graph is a polynomial function, you know the degree of the derivative is 1 less than the degree of the polynomial. So you know exactly what to expect of the shape of the graph. You might want to review section 1.6. 2, identify points where the slope is 0 or undefined. You're going to find that on your function, and then you can find it in your derivative. Examine the graph from left to right and note intervals where the slope is positive and negative. That is, note where the function is increasing and decreasing. That's going to tell you if the function is increasing, the derivative is going to be positive on that interval. If the function is decreasing, the derivative is going to be negative on that interval. And don't forget that if the slope does not exist at a point, like a corner, you might have an open circle at that point. So, for example, the function, the absolute value of x minus 3 plus 5, let's just see what that looks like. Absolute value of x minus 3 plus 5 graph. There we go. So we're at 3, 5 is the point. So if this is my function, at x equals 3, the derivative is undefined. To the left of x equals 3, slope is negative, and the slope is the same the whole time. It's a constant. So this would be negative 1. Let me write this a little different. That's not what I want to say. This is -1. This is 1. So given the corner at x on the corner, we are undefined. This is a really simple graph. We can see that we've got constants on either side. Something to think about. Now I've got another video underneath this one that is a link to this puzzle, and I'm going to walk through several graphs and derivatives in a matching game to talk about in more detail connecting graphs of functions with their derivatives. So you're going to want to look at that next.